Okay, so good afternoon for everybody. It's a little bit 2 minutes after 12 in Jerusalem. And I'm the last speaker of this meeting, which would be very nice if we would have it in South Africa. But I'm in my office in Jerusalem. And I hope this will be a good summary in a way of not all of what we heard, of many things of what we heard in this meeting. And I want to discuss the thermodynamics and the quantum master equation. This is the subject of what I want to talk about today. And it's done, all the work has been done by Idan, which is a graduate student in Jerusalem. So before I start, this is today in Jerusalem because we don't meet, so at least you can see how things look here. Here's my morning coffee at my porch, and I walked in the campus to my office. You can see it's completely empty. The students are away. So this is a sad part of that. And you can see there's a sculpture of Einstein on the way, which is relevant for what I'm going to tell you later. So this is how Jerusalem looks like today. And so let's continue from here. These are a summary of relevant papers which are related to what I'm going to talk about today, and two more people which contributed to the work. One is Amikam Levy, and the other one is Ander Tobolina, and altogether you can see here a list of 7 papers, which are all related to what I want to tell you today. So since this is recorded, this is the references that you could use if you're interested in what I'm going to tell you. So where are we? So we're in quantum thermodynamics, and these are questions that I put as a general theme of the subject, but I'm going to talk today only on consistency, the emergence of thermodynamics from quantum mechanics and the opposite. This is the topic of what I want to talk about today, and there are many other issues of quantum thermodynamics. Part of them we heard in this meeting, and some for, let's say, continue other talks. So it all started with, as I said, Einstein, which I met a sculpture on the campus today. And the idea of consistency comes from this paper of Einstein. And that's how he got into quantum mechanics, by consistency of looking at light inside the cavity and calculating its entropy and figuring out that it has to behave as a particle. So this argument, you could say, of Einstein led to quantum mechanics, and we go in a different route. We go the opposite route. We believe in quantum mechanics, or you can say this is our foundation, and we try to see how it relates to the laws of thermodynamics. And this will be, you can see the dialogue that I want to go on in this talk. So you can say our task, which is different between classical thermodynamics, that I'm going to have dynamics in my thermodynamics, and which allows to answer the typical question, the power efficiency trade-off. So I'm not going to deal with it, but that's, you could see why you want to have dynamical description, not only static. And where we start. So we start, and this is where I'm going to concentrate, is the theory of open quantum systems. And what I want to talk about mostly is a quantum Markovian master equation. And you could say this you could see has an old history, but I'm going to start with Krauss, which is 1971 paper, which defined what we call a completely positive trace preserving map. And I have that Krauss form here. And the other point, once you have a Krauss form, and then you say, okay, what's the most general Markovian dynamics that you can have? And you get the Gorini-Kusakowski-Lindblad-Sudarshan quantum master equation. And the two papers appeared in 1975. And I even have here a picture of Lindblad, which I think most people haven't met. So just for reference, this is how Lindblad looks. So this is, you could say, what we want to deal with, this structure. And I want to elaborate on this structure. So just before I do that, you could say, just collected from this meeting, different talks and different people who address the master equation. So you can say it's still a live subject. And you can say here it's the talks. So you can say there's in Ashan and Alberto and Nina and Gabriele and Anton and Marco. And these are only talks that related directly to the master equation, but there's also resource theory, which you'll say it's connected to what I'm going to say, which also relates to what I want to talk about today. So you can say, from this point of view, I'm addressing many topics that have been discussed in this conference. So let's start. So we have open quantum system dynamics, and the first assumption is that there is a unitary evolution of the universe. And sometimes this is called the Church of the Hamiltonian. So we assume that there's Hamiltonian dynamics of the system, the environment, and an interaction. This is the total Hamiltonian. And another assumption that we have, and I'll deal with it later, is that we start with an initial tensor product between the system and Beth. And once you do that, you look for a reduced description, which is this dynamical map that I talked about before. We trace over the environment of the total unitary transformation on everything. And so this defines a dynamical map. You could say the Krauss map, it's the same thing. And the semi-group property is now we impose it, that the dynamical map is Markovian. It has this structure. And if we write it like that, it has a generator, which we call the semi-group generator. We can write it as an exponent, which basically comes out of this Markovian property. So I'm summarizing basically things that are well known. And now, what we'll deal with is what I call here isothermal partition. This is where thermodynamics comes into play. And this is the interaction between the system and Beth. And just before I do that, we can say we have the 0 and second law just by construction, that the dynamical map is contracting. But you can say it reduces the distance between two density operators. And if we have an invariant of our map, that means the map doesn't change it. So then we can write this expression and we can say it's monotonically decreasing and until we reach equilibrium. So this you can say is a way to say that once I accept this view that I have a dynamical map, and I have a single, you can say, eigenoperator of my map or an invariant of my map, I'll monotonically reach equilibrium. Now, this theorem has been proved by Lindblad, and you can say it's an integral form. It's sometimes more well known as Svon's inequality, which is the dynamical form. But you can say this is sufficient to understand that a dynamical map leads to equilibrium, and it leads to it monotonically, which you could say is how we can understand this 0 and second law. Now, let's go to this issue of isothermal partition. So I have my system. Here I have a quantum system with energy levels. I have my environment, and I have an interface which connects them. Now, in thermodynamics, in classical thermodynamics, the assumption is, or the thermodynamic limit is that this interface is negligible. So I can associate all the variables either to the system or to the environment, but we know that without this interference, this interface, there won't be energy transfer from here to here. And this is what interests us. So the question is, how can we describe it in a quantum mechanical way? And what we say that the energy of the interface commutes with the energy of the system plus that. What does it mean? That all the interface can do is take an excitation from here and put it here, or vice versa, and it doesn't accumulate energy on the interface, which you can say looks quite appealing if you want to think about how an interface should look. Like anything in thermodynamics, it's an idealization, but it's a very useful idealization, this strict energy conservation, that no energy is accumulated on the interface. Now, what we'll see that once we assume strict energy conservation, then we see that the free propagator and the dynamical map commutes, which is written here. And we have seen this in this conference, and I'll tell us where. And what does it mean? Here, this is the free propagator. And I just remind you that what I'm using here is Liouville space. So I'm treating these super operators as operators in a larger extended Hilbert space, sometimes called Hilbert-Schmidt. But still, I'm using, you can say, standard ideas from Hilbert space. So I have two operators, and I assume they commute. And once I assume they commute, what we'll get out of it, and you can say this is one of the main points that I'm going to emphasize, that also the generators commute. Not only the maps commute, but also the generators commute. And that if this happened, that has very strong implications on the master equation. So to summarize what I'm doing here, I'm adding one more thermodynamic restriction to the idea of the GKLS equation, the strict energy conservation. And then I'm asking, okay, what will be the implications on the master equation if I impose this restriction? So let's see. So the framework, as you could say, is a Markovian, that the map has a generator L written here, and we can write the differential equation, our master equation, in this form. And we can decompose our generator into a Hermitian part and a dissipative part. Again, this is not completely unique, but it doesn't matter from our point of view. And what we know from the GKLS formalism, that this D part, the dissipative part, has this structure. And really the question that we can ask if we look at the structure, what are these L's, sometimes called Lindblad jump operators? And what are these kinetic coefficients that I have here before? Can I say something about them except that this is the general form of the GKLS equation? Okay, so what do we get? So let's start by making it a little bit more formal. So you can say, like many things, we have idealizations. So the best thing to do is to formulate these idealizations, and then you can argue, do you like them or not? But let's see what they mean. So what do we put here? The dynamical map is Markovian, some satisfying the semigroup property. The environment remains stationary state with respect to the environment's free Hamiltonian. So the environment is large and stationary. The fixed point of the dynamical map is a thermal state. And finally, the composite system satisfies strict energy conservation between the system and environment. So I put 4 thermodynamic postulates, and now let's see what it means. So you can like them or not like them, but let's see what we can get out of that. So the consequence from the strict energy conservation, what it tells us, that any state that has this form, it's a function of the system plus environment, is invariant of the global dynamics. And if the environment is in a Gibbs state, so then this imposes automatically that this form, as we said, this function of both is an invariant of the dynamics, which means that the system also has to be in a Gibbs state. So we got, you could say, a form of the zeroth law of thermodynamics. We know what's the fixed point of our dynamics. This, in a way, is a lot of information, as we'll see in a minute, but let's go on. So the theorem 1, which is the main theorem that we're going to be based on, says that if we have strict energy conservation, as we say here, and the initial state is stationary HE, and the environment is stationary, then the dynamical maps commute. And the proof, you can say, is straightforward. You take Gauss form and you just explicitly write what is a dynamical map in Gauss form, and you use the stationarity of HE, and you can get this condition that the two of them commute. Another way to think about it that immediately tells you why they should commute, if the bath is stationary, it doesn't matter when I connect to it. So that's why you can say I can do free dynamics, I can connect to the bath, I can do you can do dissipative dynamics, or I can do the opposite. I can do dissipative dynamics and then go with my free dynamics. This is, you could say, a manifestation of time reversal symmetry of the situation, which comes because the bath is stationary and large. So what do we get out of this? So we get out of this the structure of L, the generator. So what do we say? That if these two maps commute, then the generators also commute. So HS, which is the generator of the free dynamics, commutes with the dissipative part. And you can say also HS has to commute with the whole part, with L. So these two things have to happen simultaneously. And now, when we know the two operators commute, this tells us that they have a common set of eigenoperators. So I'm reminding you again, I'm using spectral analysis, but my operators are super operators. But still, I could use the same ideas that we have from linear algebra, that if two operators commute, they have a common set of eigenvectors. In this case, the vectors are eigenoperators, because this is what the super operators operate on. So we have this condition. And then we can ask, okay, what are the eigenoperators of the free dynamics? Because this is something that's easy and we understand. And we can say that the free dynamics has two types of invariant of eigenoperators. They're invariant operators, which are degenerate, which are just the projections on energy levels. So there are the NN here. I wrote them as pi n, as NN, and these are stationary under the free dynamics of my system. So this is one type, and the other one is non-invariant operators, which are basically the transitions between state N and state M, and they satisfy an eigenvalue type equation. If I do free dynamics on these operators, I get e to the power of the Bohr frequency times the same operator. So they're eigenoperators of the free dynamics, and then they're defined by the Bohr frequency between energy levels n and m. I just want to remark that what I'm going to use here, I'm going to assume that this structure is not degenerate. So I don't have, at this point, two Bohr frequencies which are the same. Otherwise, you have to treat this in a little bit more careful way than what I'm going to show here. So now we know quite a lot, because we know what are the eigenoperators of the free dynamics. And now we can say, okay, these have to be also eigenoperators of my dissipative part here, because they commute. So this already says that I know a lot about my dissipative part of my generator only by this statement. So let's see what are the consequences, which tells me exactly what is the structure of L. So in general, you can say L has a Hamiltonian part, which I'm not dealing with, and the GKLS part, which has here. And you can say this part is divided into two. It has the invariant parts, which are the pi operators, and it has a non-invariant part, which are these F operators. So I just put these operators into the GKLS equation. And now, if you want to, you can check, because these are, in a way, projection operators in Hilbert-Schmidt space, that if you stick an Fk here, it's an eigenoperator of this GKLS equation. So just a consistency check. Now, once we know that this is the structure of our GKLS equation, then we can do a little bit of manipulation. And we can use diagonalize this part here by choosing a linear combination of this degenerate state, because it's not determined yet, and get a diagonal part, and we get the form, which I like, of the dissipative part of the GKLS equation, which comes from the strict energy conservation. So what do I have here? I have here two parts. I have these FKs, these jump operators here that I have here. They're going to operate on this bullet. And this is one part. And then I have another part, which is composed from this invariant set, which is double commutators. These V's are Hermitian. So the GKLS equation becomes a double commutator with these V's, and these V's commute with the Hamiltonian. So now let's look at this a little bit more carefully. Now we have these kinetic coefficients, and now we can impose that the stationary state is a Gibbs state. So we can get out of this detailed balance. You can say the Gibbs state is an invariant, and that immediately says that we get the ratio between K and minus K is e to the power of beta omega, where omega is this Bohr frequency of this transition. So we didn't get this completely, but up to a factor, we got the kinetic coefficients. And now we have the other part, which you can write it slightly in a different way. You can write it the dissipative part here, or the dephasing part, which I like to call it, is a double commutator with a function of the Hamiltonian. So why is it dephasing? This is going to kill coherence, but it commutes with the Hamiltonian, so it doesn't change the energy structure of my system. So what we see that we get, our dissipative part has two parts to it. The first part will cause equilibrium to a Gibbs state, and the second part, which in a way is independent, and you can say it's undetermined in this case, but you could, is a part that causes dephasing, which has a structure of a double commutator with a Hamiltonian. And just to comment, a structure like that says that if I would measure energy in a weak measurement, I would get the same structure, because a weak measurement, the back action can also be described as this double commutator. So if we go back to Eric's talk and we say, okay, we want to measure energy on the way, we could add a term like that that would look like a dephasing term in the GKLS equation. And just to comment, there's a very nice paper by Robert Alitsky, which in many ways you can say there is a lot of similarities with what we showed here, but using a different assumption. He also tries to get the structure of the GKLS equation. This was a master's thesis of Robert Alitsky with Kusakowski. And his assumption is that you get detailed balance. So he gets a similar structure. He doesn't get this part here, only assuming that the fixed point of the map is a Gibbs state. So you can say that connects to this idea. Okay, so we did some, you could say, we put postulates, we did some mathematics, and we got a structure of the master equation, which is quite useful. But then you can ask, okay, how should I think about these postulates? Maybe there are two restrictions. There are idealizations. So let's kind of go through them and look what we put here. So the first thing we put time reversal symmetry breaking. This is the way we did it. We put Markovian dynamics, which breaks the symmetry. And we know that if we take mechanics, we have time reversal symmetry. So where does this symmetry breaking come from? And what my way of thinking about, it's enough we put a partition and we already lost, broke the time reversal symmetry. So any partition, which means that we lost part of the information in the world, we are not allowed to measure everything, already tells us that we broke the time reversal symmetry, at least from a subjective point of view, what I can do. So this second assumption is it's Markovian dynamics. You can go from this and you can say that once you assume Markovian dynamics, it means that your system and environment are in tensor product all the time. So you kill the correlations between the system and that. Now, you could say that's too restrictive because if you wouldn't have correlations, energy wouldn't be transferred. But this is kind of a, you could say, a loose idea that the environment kills these correlations extremely fast. So there is a certain time scale associated with, you could say, the statement, which is typically called coarse graining in time. So if we put a coarse graining in time, you can see Markovian dynamics can be exact for very short times, but there's a certain time that we can consider it. This is how we think about it, or at least I do. So once we have a time scale, then we have also an energy scale, which is h Planck's constant divided by time. So this already says that our strict energy conservation is not so strict. It's up to this coarse graining time. So it means that want to think about that the energy that's accumulated in the environment can fluctuate up to this time scale, delta E, and still the same structure that we had will be useful. Now, so let's see if these assumptions are empty. The first thing, can we find examples that these assumptions are okay? And the first example that I bring here is the collision model and its original form. And the idea is that I have particles in a gas, in a dilute gas, and they collide. And the collision can be described by an S matrix. And the S matrix, when the particles get close, there's an interaction, and then they fly apart. This interaction goes away. So eventually you can say a scattering idea says that there's no accumulation of energy in the interference between the two particles that collide. So an S matrix has, by construction, strict energy conservation between the system, my particle, and the environment, which we assume is thermal. So we can immediately get the dynamical map that we get from the collision model, which is this S matrix, and we trace over the environment. And then we say if we have a certain collision rate, which has a time scale tau, we can write the dissipator as, you can say, this is what did I do here? I should have thought I put S here, never mind. It's okay, there's a typo on this line here because I shouldn't use it like that, but never mind. What does it mean? If I think about the collision model, I can think the rate of change is the state after the collision minus the state before the collision times the collision rate. So you can get immediately a master equation out of that, which is called the dilute gas model. And you can get a time scale, which is the collision rate. Some people call it the Poissonian model. That's how it's referred in Lindblad's paper. And I found the original reference, which goes to Robert Kauplus from 1948. So his brother is more famous because he got the Nobel Prize, but Robert Kauplus did his PhD with Schwinger, and they already, you can say, originated this master equation, which comes from the collision model. And here you can see. So this is something that now we use quite a bit, not as its original, because the original scattering matrix commutes with the sum. And what we learned that if we want to use a collision model, we have to account for the switching, how much energy we need to put the interaction and turn it off, and the work that's involved with that puts the thermodynamics back into order. But in the original model, thermodynamics is in order because the S matrix commutes with the sum of energy. Okay, so at least we know that our assumptions are not completely empty. Here's another very common typical derivation of the master equation through the weak coupling limit. And sometimes this is called Davis construction, which is, you could say, from a mathematical point of view, is a careful derivation of the weak coupling limit. We heard about it in this meeting already. And the step one, you go to the interaction representation, and then you do a perturbation theory, and you take the partial trace. And step three is the one that has mostly been criticized as a secular approximation, which leads to the GKLS form. And if we do that, we get this, that the free propagation and L commute. So one way to think about it, that the secular approximation works like an energy filter. It only takes into consideration the parts that basically keep the strict energy conservation, because we can go in reverse. We can take this statement here that the free propagators commute, and we can get out of this the strict energy conservation assumption. So you can associate the secular approximation to something that we can, not some mathematical obscure thing, but something more physical, that it's related to this idea of energy conservation between the system and environment. And here's this paper of Davis, which we already heard about. So it also fits this same structure that I'm talking about. Okay, so just to intermediate summary, what does it mean? That L does not mix population with coherence. This is one thing. And the lump shift Hamiltonian has to commute with the bare system Hamiltonian. And now if we think about local versus global master equation, which is another issue that has been raised. So to be compatible with thermodynamics, only global can do that, because the only global ones keep the strict energy conservation idea floating. And the other two things, that in heat transport, the existence of coherence, and then there's another point which is raised here: can we find exceptional points in open system dynamics? And I'll talk about this in a minute. So here's a very nice problem of heat transport. This is an absorption refrigerator. So we have three baths. We have a cold bath, a hot bath, and a work bath. And you can say the way this works, if I get energy to flow from here to here, on the way I pick up energy from the cold bath, or excitation, it's a better word to say. And this, generally I am cooling the cold bath, and entropy generation works because I'm taking this temperature as the highest temperature, so I'm moving heat from the highest temperature to an intermediate one, and on the way I'm picking up excitations from the cold bath. So in order to realize that, I have to have a nonlinear interaction. You can say I'm taking an excitation from the cold bath, I'm taking an excitation from the work bath, and I'm generating an excitation of the hot bath. So this is my interaction Hamiltonian. You can say I have energy filters here, and I can work in resonance condition. And now you could ask, and the question about this absorption refrigerator, does it have coherence or entanglement? The original question was, as it works in steady state. So the first claim said that it has, people solved the master equation, they used the local master equation, and they found in the steady state that it generates coherence. But now, if we think about it, I have three baths that are stationary, and we know that the stationary part of my system won't be a Gibbs state because I'm connected to three baths, but on the other hand, the same structure of the master equation, it should commute with the system Hamiltonian. Therefore, the same conditions we have, and we should get no coherence in steady state. So this has been found by Luis in this paper. In a way, for this model, they could diagonalize and get the global master equation, and they found the same conclusion that here we could get from general principles. So this tells us that if we just have heat transfer, different baths in the system, in steady state, we won't get coherence. Okay, so now, let's say I want to get coherence. So how do I do that? I drive my system. So if I drive my system, then I can get coherence out of it. And we want to extend the same ideas and to get the master equation from a driven system. And what do I have here? You can say I have my system Hamiltonian. I have a controller, which is this green part here. I have my environment, and I have two couplings. I have a coupling between my system and the controller, and I have a coupling between the system and the environment. And you can say, as before, the total unitary is just of the total Hamiltonian, so I can treat the whole thing, everything as a unitary dynamics. And then we can do very similar to what we did before. We can assume initial tensor product state between everything, that we're in a state like that. And we want to get the reduced dynamics of our system, and again, assume Markovian dynamics, and to get the generator. But there's one difference between what we did before, that the controller is non-stationary. So this green part here is non-stationary. It means this part here has coherences. And I think we heard that. So once I have coherence here, I can transfer it here, and this will what we'll see in this derivation. Okay, so what do? I first take these two parts together, this Hamiltonian, and call it my extended system, and then I'm in the same situation as I was before. I have a large environment coupled to a system, and I can get the, you can say, the GKLS equation for this part. And then I'll do another reduction and get rid of the control. So you can do that. Now you can say I have two double strict energy conservations. You can say that this interface, it conserves energy between everything here and here. And the other interface, this one here, also, you can say conserves here. So it means energy that I lost here, I'll find itself either here or here. So I have the same idea, but doubled. And then you can get out of it that the free propagator of C will commute. And also the free propagator U0 and U will commute. And U0 is this propagator of, you can say, my extended system. And then you can say that's, I can write this propagator, which I'm interested in, of my system plus the controller. I could go to the interaction representation and take this UC out of it and get this interaction representation propagator of the system plus the controller. And it also should commute with the total unitary. So using these ideas of commutation relations here, which I summarized them here. So this is what I would call autonomous drive. I made a controller, put it in some non-stationary state, and then just looked at the dynamics of my system. And I can move my controller to a semi-classical idea and say, okay, my controller is just some time-dependent field that does the same thing. And you can say I can, in a certain limit, these things become equivalent. So this is what external drive and an autonomous drive becomes equivalent. And it's important to understand that, because that means that I can look at the eigenoperators of the free propagation of my system, and I know that this is what I'll find in my Lindblad operators. So the eigenoperators of the free propagation will constitute the jump operators when the system is externally driven. So what I get out of it, I get a way to construct the master equation when I have an external drive. And this is what we call the non-adiabatic master equation. We got it originally in a different way. We got it through, you can say, Davis construction. But what I have here, I have a Hamiltonian, time-dependent Hamiltonian. Here it's a bath, not an environment, but never mind. And I get this commutation relation. And out of that, once I know what are the eigenoperators of the free propagation, which, as we see, it's not a completely trivial task to find them because there's time ordering here, I can construct my Lindblad master equation, which will have the same structure as before, where these F are my eigenoperators of the free propagation. And the fixed point, what happened here, will become the instantaneous attractor. This shouldn't have been F here. And so I get a fixed point, which is time dependent, because my whole equation is going to become time dependent with a drive. So I don't get a fixed point, I get an instantaneous attractor here. So this looks a little bit abstract, but so I want to show an example. And the example is, as usual, the most simple case that we can think about. Let's think about the qubit, and let's think about the time-dependent Hamiltonian, where I both drive the z direction and the x direction. So I have two fields, omega and epsilon. And now what I'm going to do, in order to solve this, I'm going to use an operator base of three operators. I can add the identity, which will be time dependent. So this will allow me to solve the time ordering problem. So my operator basis will be the energy, the Hamiltonian itself, the Lagrangian, and the correlator. And in this case, L, you can see, looks very similar to the Hamiltonian, just the epsilon and omega are switched, and I have a minus sign here. And you can see that these two operators are orthogonal, and C is just the SY direction, which I didn't have before. And I can get a time-dependent Rabi frequency, which will be the energy scale of this problem. And what's mostly important in this case, since we're talking about non-adiabatic cases, to define a diabatic parameter, which tells me how fast I'm moving relative to the energy scale of my system, which in this case becomes this expression here, omega dot epsilon minus omega epsilon dot divided by omega cubed. You can see this is dimensionless. And then when it's very small, it's adiabatic, but this can be as any number you want. It can be very large if you're doing very strong non-adiabatic driving. So what I should emphasize here, that to get something non-adiabatic, I needed the Hamiltonian at different times doesn't commute. So that's why I built a structure like that. And so I can have a Hamiltonian that doesn't commute at different times. Okay, so I can write the free dynamics in this operator basis of US. And what's nice about it, that you can see I got a constant matrix here because I used the time-dependent basis. I could get rid of the time dependence. I got a constant matrix here, which means I can diagonalize it. Here I have my non-adiabatic parameter here. And if I can diagonalize it, I can get the eigenoperators of my free propagator just by diagonalizing this matrix. Here I have a scaling factor, which is in this case irrelevant. So this is the solution for the propagator, but in a way you can see I just have to diagonalize this matrix. So what do we get out of that? We get the eigenoperators of the free dynamics. So you could say there are three. There's chi and sigma dagger. And chi is composed of the Hamiltonian and the C, the sigma y, with the parameter mu. And you can say when mu 0, when a diabatic case, this chi is only the energy. And you should think that this chi is Hermitian, will be the invariant. So this, if you look at this, this can cause dephasing. So this is what this term is, which is Hermitian. And the jump operators, you can see the I here, which are non-Hermitian, have everything here. They have the Hamiltonian, they have this Lagrangian, and have C built into them. This is at time 0, they're all time dependent. So these are the eigenoperators of my free dynamics. And as we said before, they would constitute the GKLS equation. Now, if you look at the eigenvalues, there's 1, 0, which is associated to chi, which means that this is an invariant. And there's lambda 2 and lambda 3, which are complex conjugated, and you can say what they have is the Rabi frequency times kappa, which is this term here, which is a non-adiabatic correction to the frequency. And what's important here, when we're driving things very fast, a non-adiabatic parameter is large, the effective Rabi frequency is larger. So this will have implications in the master equation. Now, here's the master equation that we get out of it. As I said before, these are the eigenoperators. So this part I didn't include. I only include the jump part. So it looks like a standard master equation for a two-level system is sigma and sigma plus. Just the definition of sigma and sigma plus are different. And we have kinetic coefficients, which are functions of alpha, a modified frequency. So you can say the detail balance condition is not a standard one, it's modified by the drive. So if I drive faster, I have a higher frequency. So this has consequences on the detail balance form. So this is the master equation that I would get out of this construction. Now, you could say immediately, chi already has coherence built into it. So the invariance has coherence, and the instantaneous attractor is composed out of this chi. So it means, in this case, the driving is going to lead to coherence. Now, here's the instantaneous attractor. You can say it's built out of chi. In a two-level system, it always can be written as a Gibbs state with, you can say, a modified frequency here on alpha instead of omega. And I can calculate the entropy production related to this instantaneous attractor. And we know it has to be positive. So we can write it like that. And as we expect, if we drive the system, what we can see here, if we drive it faster, it's going to be more dissipative, and the entropy production will be larger than if we do a slow drive. So in this case, it's a problem of thermalization that we look at. And we can write the entropy production in something which would look like a generalized Onsager formulation, force times flux. And here's the definition of the currents. And the forces, you could say, are the difference between an effective temperature, inverse temperature, and the temperature of the bath. And you could say at high temperature, it's not, I can recover something that looks very much like an Onsager relation. Now, I see I'm talking quite a lot, so I'm going to almost finish. I want to just talk about 2 points which I think have been raised recently. One is about exceptional points. So exceptional points are problems when you can say I can diagonalize my dynamics, my dynamical equation, in this case a master equation. Now, in principle, if you have a non-Hermitian matrix, you can find situations you can diagonalize it, and then you get, in the points where you can diagonalize it, you can get a degeneracy that's called an exceptional point sometimes. And what's interesting there in exceptional points, it's not only the eigen value are the same, also the eigenvectors are the same. So it means you lose a solution at an exceptional point. So now let's try something in the same problem that we have. I have a qubit, here omega and epsilon, and I'm adding pure dephasing, like that, but on H. So I'm adding pure dephasing, and I'm looking at my master equation. So my master equation, I have a driven system and pure dephasing. So as I said, here's my master equation. And you can say here I have a constant matrix. But if you check it, you can find points that you can't diagonalize it, and you can find exceptional points. And here's an exceptional point if mu is the square root of 8, and this dephasing is the square root of 100, which is 10. You can say it's a very large value of dephasing. We get here, this point here, a triple exceptional point. So you can say, okay, what is the issue here? How can I find an exceptional point when before I told you that you can't have that? So the reason is that this dephasing term originates from a non-thermal bath. It has infinite time scale. Sometimes we call it a singular bath limit, and that doesn't follow our rules. So we know already that if we don't follow our thermodynamical rules and we take a resource that's outside thermodynamics, in the sense it's a singular bath limit, then we can get exceptional points. If we go back to our original master equation, which has this driving here, and we can see that as we have here the invariant part and the coherence are separated. And if you look at this matrix, you can always diagonalize it and you don't get an exceptional point. So this is one point. And now I go to get to my final conclusions. I'm sorry that I took you a little bit almost beyond the time, but never mind. What did I say today? Many things, but I'll try to summarize. That we're looking for quantum dynamics which is consistent with thermodynamics. And the first thing that I talked about is a stationary case. So as we said, the unitary part and the dissipative maps share a common set of eigenoperators. And you could say this even goes beyond the Markovian limit. I don't need to show this, the Markovian limit. Now, in the Markovian limit, the generators also commute. So we get time translation symmetry here built into that. And also the reverse is true. If these two generators commute, that means we get strict energy conservation. Now we found out that the fixed point of the map is a Gibbs state. The lump shift Hamiltonian also has to commute with a free propagator. We found out there's no coherence generated in steady state if we have multiple baths. And L is normal, there are no exceptional points. So this is on the stationary case. On the non-stationary case, or the driven case, we now know that this unitary, or in the interaction representation, share a common set of eigenoperators. The generators, these generators have to commute. It's written like that because of time ordering. Now the fixed point is an instantaneous attractor. So it's a moving target and we can play with that. We can kind of pull a system by its nose, or a carrot, sometimes it's called. Now, the entropy production rate is proportional to the distance from this instantaneous attractor. So we can have a way kind of to control that. Coherence is generated. And this comes to what we know from resource theory, that coherence is a resource. We transfer the coherence from the drive. It's not generated spontaneously. And finally, the external drive is equivalent to an autonomous non-stationary control. There is a limit that we can connect these two things. And at this point, I'm going to stop. So thank you.
All right, thank you very much, Ronnie, for this interesting overview and interesting master equation indeed. So we have several questions. So let me read it. So yeah, there's a first question, Anton, which is quite long, but then he said, like as a comment from, I mean, he said, yeah, okay, there's a relaxation of strict energy conservation condition to an approximate form. Partially answers the first question. So it was when you were talking of coarse graining. Due to the coarse graining, you have you loosen a little bit the strict energy condition. So, but so his second question: do you assume that the Gibbs state is the only stationary state? It seems that everything works if it is a stationary state.
Okay, so I don't have to assume a Gibbs state. I can assume that the bath is stationary. This is all what we need with respect to the energy basis. So that's why you can extend this idea if my system is connected to more than one bath, let's say 2 baths, and I have a transport. You can say I have a super bath that's not in a Gibbs state. So You can say the structure of the master equation will be the same, but will be different. You won't have detailed balance. You'll have a different conditions of the kinetic coefficients.
Okay. Then there's a question from Ivan. Hi, Ronnie. Thanks for the very nice talk. I am curious about the condition in the tricycle that the work bath is hotter than the hot bath. Is this a necessary condition for absorption refrigerators, or is it particular for your model?
Here. So you could, okay, first just anecdote, the absorption refrigerator was invented by Einstein and Szilard and was patented, and they understood, you could think that they would understand what they're doing. So you could say the analysis is you need to, if you look at a system like that, you have to obey the second law. So you have to see where you're generating entropy. So if I just take, you can say heat from the cold bath, I can't just put it in the hot bath because you can say entropy, I'm going against the second law. So I have to, that's why you need this triple coupling that you have here. That's why the hottest temperature is this work reservoir. And you can say the limit would be, this would be infinite temperature. Then you could say I can take energy out of a bath with infinite temperature with no entropy cost. So it's pure work. It's equivalent to pure work. But if it has a temperature, there's a certain entropy cost that I take out of here, but then I put it into the hot bath, which is colder. So I gain entropy. I'm taking heat from a hot bath and putting it in a colder bath. So if I gain entropy, then I can, you can say, slave this process to another heat flow from the cold bath. And if I do it together, I can preserve the second law. This is how an absorption refrigerator always works in this fashion. So all what you have to do is kind of figure out where the entropy comes and where it goes. So the hot bath, you can say, is the entropy sink in this case.
Okay, nice. So we have, Marty, you can talk. Then I come back to the question written in the Q&A.
Hi, Ronnie. So I have a first question, which is, so because in this instantaneous attractor that in general is not of Gibbs form, but you discuss it in the case of that you have non-commuting dynamics. So I was wondering, in the very simple case that you would only change a frequency, would the attractor also, would it be the normal, like the instantaneous Gibbs state, or would it get renormalized as well? Or for example, this detailed balance, is it satisfied or it's also modified in the simple case of commuting dynamics?
Okay, first of all, you're right. Here, let's see the instantaneous attractor. Here it is, over here. If they commute, you won't get this, it would be, the instantaneous attractor would be the Hamiltonian.
Okay.
Or a function of the Hamiltonian. Now, what you're asking, will I get a modification of the frequency? Exactly. I think yes. Mm-hmm. But I think I think the mu, or the non-adiabatic parameter, would also be here.
Yeah, I'm asking because in many models of heat engines, you just would change the frequency, right?
Yeah, that's adiabatic, but now we want to go beyond adiabatic. If it's adiabatic,
you could do this fast. I mean, you could be in contact with a thermal bath and just change the frequency. I mean,
yeah.
Mm-hmm.
So if you look at mu, You know what? It would be 0. Because if epsilon if epsilon is 0,
I see. Okay.
It commutes. So mu would be 0. So you wouldn't get them. So we have the answer. It won't change. It will be the Hamiltonian.
Okay. Okay. That's interesting.
It's a result of they don't commute.
Okay. Okay. Thanks. And then second, I have a comment. Sorry, I have to. So I go back to this to the quantum absorption refrigerator, because I mean, you mentioned this paper of Louis, right? That they show that there's no coherence in the steady state. But then there's another paper by Louis, and also we did a paper with Patrick Potts in 2017, where we were comparing a model like this, but with harmonic oscillators. But there you can solve everything exactly. And you can compare it to the exact dynamics, and you can check, right, these kind of statements, whether the global master equation or the local master equation. And there we really saw that when this interaction, when this G is weak, the local master equation gives you much better results compared to the exact dynamics. And I mean, Anton also commented this in his talk. I mean, you can derive the local master equation in a rigorous manner. So I find these very strong statements a bit dubious, because when you would compare it to exact dynamics, it's not so clear that you will indeed find, for example, no coherence in the steady state. Or so maybe it says something about the assumptions that you are making, right? Not about the real physics, let's say.
I like your question, because I think this is a very important discussion. We really can't, that's why we need not coffee, a few bottles of wine, and we can maybe resolve this issue. But I would say there are a few points here. First of all, what I showed, you could say I put assumptions, and I say, okay, what are the consequences of the assumptions? And you could say you agree with them or not. And but then you could say, okay, I can do derivation. I can derive the master equation, and I can check it to what is called exact result. And this is a little bit, you have to be a little bit careful about that. Because what does exact result means? Exact result means that your bath is harmonic. It's a normal mode bath, or you can say a bosonic bath, which we can simulate in a cheap way, and we can get from that results. But it's in a way, you can say we can get many good things out of it, but as a thermodynamic bath, it's a very bad bath, because it doesn't equilibrate.
No, I don't agree with this. I mean,
it doesn't equilibrate. There's no way, because it's normal mode. If I take energy from one mode, there is no way that this bath will equilibrate by itself. It has no nonlinearity. So this is something that you can find in Robert Alitsky's book. It's a thermal bath, but it has very bad ergodic properties.
Well, but if you look at the system, for the system is a good thermal bath. I mean,
maybe. So this is where I don't always agree with that, because I would say in many cases you can get results that rely on the fact that the bath is harmonic. So I like this. There's a paper by Plenio, which did also compare to harmonic baths and look at the same problem of a local versus global master equation. And you can see the global master equation gets into trouble when the two intermediate beads are in resonance, which is where the secular approximation breaks down. But what did he find out there? When you're in resonance, you start to correlating the two baths. So the assumption that the two baths are uncorrelated breaks down also. So then you could say, okay, maybe I can get away with the local master equation, but you could say that in this case, the assumptions using this type of harmonic bath break anyway. So, so then I would say using, you could say to compare to exact result, you have to be a little bit more careful than what it means. I think if you could compare to a spin bath, what would happen there is different.
I'm not sure of that, but okay, I see your point. And
spin bath has very strong ergodic properties. We know that.
Yes, yes, no.
Eigenvalue thermalization kind of, and then okay, this I think is an open question, and maybe that should be the subject of the next meet.
Yeah, no, I agree. It's a good point. Yeah. Okay. Mm-hmm.
Okay, there's one question from Gonzalo, also exactly on that question. Sorry, Ronnie, in the three-cycle model, does not the circular approximation break down for small g coupling between the three qubits?
Yeah, so it's the same issue. If you're in resonance with the three baths and you do it, if they're bosonic bath, you could be in trouble. You can correlate everything. So.
Okay, now there's a question from Gabriel. Very nice talk. Is it possible to extend the construction of the first part to non-Markovian evolution?
This is a good question, and the answer is yes. Because if we see where we started, this strict energy conservation, here, I'll put it here. What it means that the maps commute. When I look at this line here, I didn't put the Markovian assumption yet. Only when I go to generators, I put the Markovian assumption. So this idea is that even for a non-Markovian map, you know its eigenoperators. Now you don't know you can say its eigenvalues, they can become time dependent and they can be all kinds of things, but you know the structure, even for a non-Markovian case.
Okay, so yes, is a question from Marco, but then he said, okay, the question goes along the line that we already discussed, so related to the three-cycle model. And there's a last question from Loris. So, hi, Ronnie, thanks for the very interesting talk. Regarding the driven case, if you compare prediction from your formulation of non-adiabatic master equation with the exact treatments based on the specific model of a bath, for instance, caldera-Leggett kind, do you expect deviation, sorry, if any?
Okay, here's the non-adiabatic master equation. So you can do, and we did that, I'm saying we did the standard thing that we took a bosonic bath and we compared to exact results, and we tried to see that we can reconstruct the results of the master equation. Not for a spin system, we did it for a harmonic system, which is, so it's a harmonic oscillator coupled to a bath of harmonic oscillators, which is a linear problem and solvable. And what we do here, we sweep the frequency, and then we can see that we can derive the master equation, and we can compare it to what we get from the numerical integration. So we could reconstruct that. There's only a problem here, which is just a numerical problem. it's much more difficult to do. And the reason is you sweep the frequency. And so it means you change the resonance conditions. And we know what's important in a bath, the modes that are important are the modes that are in resonance. And the modes that are not in resonance, you can forget about them. So when you just try to simulate a harmonic or a bosonic bath, you can mostly include in your calculation the modes that are in resonance. But in this case, you're sweeping. You're changing the resonance conditions, so it means that if you're sweeping a lot, you're changing your non-adiabatic parameter is large, and you're going through a large frequency change, your bosonic bath becomes enormous. So it just is technically harder to do, but we did as best as we could. So when we compare it, we can converge.
Okay, and so there's one final comment from Gonzalo. So thanks, Ronnie. I have a final comment. The local approach seems to me to be compatible with strict energy conservation with respect to H0 instead of H-ace.
No, I don't think so, no, because the interaction term between the local part and the other part doesn't commute with the interaction with the bath. It's not correct.
Okay. Okay, so I think we don't have any more questions. So we can conclude. So thank you very much, Ronnie, for your time, for this very interesting talk and for the discussion. And now we are, so yeah, just one thing that I keep saying after at the end of